All right, we are going to continue our world of energy. We're going to do another example on what happens with a non-uniform force. And we are going to eventually dive into power and get a look-see at what makes things tick. So here we go. So last time when we were looking at work, we said, okay, well, work is force dotted with distance. If our force is constant over our distance, and what we have is we have this rectangular region right here. And that rectangular region corresponds to the work that area inside does. So if we had a non-uniform force, well, the area underneath is going to give us work. Well, let's think about how that equates with our springs. We've done that Hooke's Law lab now. So if I look at my position and my force, so force versus position graph, and I have that line, that kx, if you will. And I wanted to find, okay, well, what is the work done here? Well, I would just drop that perpendicular, say, okay, this is some distance x, that's some point kx, right? The area of a triangle is 1/2 base times height, so our work is going to be the area of this triangle right here. And so that's going to be 1/2. Our base is this distance, so that's x. Our height is this distance, which would give us kx. So the work done by the non-constant force is 1/2 kx squared, which is kind of cool if you think about it that way. And we could do this with calculus. We could look at, mathematically, we are looking at the integral of force with respect to position. So our work, if we're using calculus, is again the integral of the force in the x direction with respect to the distance in the x direction, so with respect to x. If we go into multi-dimensions, there's a trick for that. Don't worry, we're not there yet. Although we did do an example of that last time with this particular force. So let's get on to the nuts and bolts of where we're going. So we have a medical procedure where we have to take and put a needle through the skin. So if we mapped the forces that are applied, this is the part that matters to us. I realize that we are not a medical academy, but the part that matters to us is this graph right here. We have a force versus position graph. If I want to know the work done by this non-uniform force to get the needle through the skin, here's what we've got, is we can break this shape up into all of these nice, pretty little geometric areas. So we've got a triangle, a triangle, a triangle, triangle, a triangle, and a whole bunch of rectangles too. So if I wanted to work this out, literally what I'm going to do is I'm going to calculate the area of each of those regions. So the area for region A, so let's see, a better way of maybe describing what we're calculating here is that the work done by the force for region A is going to be 1/2 our base. So we've got 2, 4, 6, 8. So this happens at 8. So 1/2 8 times my top up here is 12. So I've got 1/2 base times height, or 8 times 12. The work that's done for region B is going to be a rectangle. So this is going to be 2, 4 across. And we are, as we can see right here, only 6 high. The work for region C is going to be 1/2 my base. Now my base is still just 4 times my height. Well, I'm going from 6 to 12, so that is 6. The work done for region D Got to look at my base. This is going to be 2, 4, 6. And I've got to look at my height. My height is also 6. The work done for region E, I've got 1/2. My base is going to be 6. My height is going to be, well, if you'll notice, these are in ones. So it's going to be just 1, 2, 3. So just in case you haven't noticed, the X scale spacing is in groups of 2. So each square is 2 units. The Y scale is 1 unit spacing. Now this is a common trick in order to just keep people on their toes, because you're going to try using 90% of the time the same scale for both. So this is a trick that's used frequently in science classes to see if you're actually paying attention to what the graph is telling you and not just making calculations by rote memory. So be alert. Okay, the work done by force F, that little region here for F, is going to be 1/2 base times height. So I've got 1/2. My base is 2 units across. My height is only 1 unit up. If I look at the work done by G, that is going to be 2 units across. And we are 6, 7, 8 units up. The work done by H is 2, 4, 6 across. And again, we are 8 units up, so 6 times 8. The work done by I is going to be 2 units across, and we are 8 units up. Now, honestly, we could also break this as one big space right across there. It's an option. Your breaking of the shape does not have to match mine. Work in J is going to be 1/2. My base is 2. My height is 1, 2, 3, 4. So 4 squares tall. And then the last one kind of lingering over is the work done for K. That region is going to be 2 across, and we are 12 high. So what do we do with all of these regions? We add them together and get the total work done. So our total work here is going to be 1/2 of this. So I'm going to have 4 times 12. That's going to be 48. I'm going to have 24. I'm going to have 12 from C. I'm going to have 36 from D. So E is going to be 9. F is going to be 1. G is going to be 16. H is going to be 48. 9, or I is going to be, and we're going to have 4, and then we're going to have 24. Now, if we've done all of our calculations right, and we add this all up, we are going to get 238. Now, I have to be careful because this is not joules. How do I know it's not joules? Look at my units right here. That is millimeters. Millimeters. Now, typically we have to get things in terms of meters, right? So to get this in terms of meters, I would have to slide this over 3 spaces. So if I slide that over 3 spaces for every single one of my calculations, I get 0.238 joules. So you do have to watch your units, make sure you're doing the correct calculations, and move your decimal as appropriate. So, if a force is doing work in a certain amount of time, we could calculate what we refer to as the average power. Power is the work done divided by time. It's in a joule per second, which is known, insert bad physics joke here, as a watt. A watt? Yes, it's a watt. Okay, so if we were wanting to know what is the instantaneous power, or what is the power that happens right then, our instantaneous power, well, what we're going to be doing is we're going to be taking that work done over an incredibly tiny period of time. Now, if that screams, hey, that's probably a derivative, that is true. It is the derivative of the work function with respect to time. So now remember that work is force dotted with your displacement, right? So if I'm looking at the derivative of work with respect to time, I take the derivative of this other side. So what I could say is that that is going to be my force times the derivative of the displacement with respect to time. Derivative of the displacement with respect to time is the velocity. So it could be the dot product of the force with the velocity, which would be the force applied, the velocity direction, cosine of the angle between them. Power is a scalar. Power is a scalar. So if we want to look at an example here, I believe we have time on this video for this. We have a block that is moving with uniform circular motion. Everybody's favorite. So that cord tied to the block, it's anchored to the center of a table. Okay, so let's think about what this is going to look like. So I have a circle, a little bit badly drawn. You guys have seen worse. I have a block that is on that circle. So there's my block. And there is a cord that is anchored to the middle that is exerting a force on that block. So on that block, I have a force pulling in towards the center. Now I not only have that force, I have this speed right here going up. So if I want to look at the power, power we said is the force dotted with the velocity. Okay, so let's take this single position where this block is currently sitting. So my force is going to be to the left. My block velocity is up. So the angle between them is 90 degrees, because remember your velocity for uniform circular motion is always tangential to the circle. That force, since it's on the cord, it's always going to be to the center of the circle. Cosine of 90 is 0. So the power due to the force on the block from the cord